to Copilot Podcasts. A rule that governed all of computing for 60 years, every chip, every laptop, every smartphone has been lapped. Not nudged past, not gradually outpaced. Lapped. Today, we're getting into how AI has blown past Moore's law, what's actually driving that acceleration, and what the next 5 years look like based on the data we have right now. By the end of this episode, you'll understand why this moment is different from every previous tech hype cycle and what it actually means for the world you live in. I've got someone here who has been deep in this space, and I want to start with a question that sounds simple but really isn't. What even is Moore's law, and why does it matter that AI is breaking it?
So, Moore's law goes back to 1965. Gordon Moore, the co-founder of Intel, made this observation that the number of transistors on a microchip roughly doubles every 2 years. And what that meant in practice was that computing power would keep getting better and cheaper on a very predictable schedule. For about 50 years, that prediction held. It's why your phone today is more powerful than a supercomputer from the 90s.
Right, and it wasn't just a prediction, it kind of became a self-fulfilling prophecy for the whole industry.
Exactly. It was almost like a social contract. The entire semiconductor industry organized itself around that 2-year doubling cycle. But here's the thing. According to EE Times, Moore's law started breaking down in the early 2000s. As transistors got smaller, you hit physical limits. Rising power density caused thermal problems, clock speed stagnated. The law that drove 50 years of progress started running out of road.
So the engine that powered the whole digital revolution started sputtering, and then AI shows up.
And AI doesn't just pick up where Moore's law left off, it completely rewrites the playbook. Jensen Huang, NVIDIA's CEO, said in an interview with TechCrunch that, quote, "Our systems are progressing way faster than Moore's law." And he's not just talking about transistor counts. He's talking about the whole stack: architecture, chips, systems, libraries, algorithms, all innovating simultaneously.
Okay, but I have to ask, NVIDIA is the most valuable company on Earth right now, largely because of the AI boom. So when Jensen Huang says NVIDIA is surpassing Moore's law, how much of that is marketing?
That's a fair and important pushback. TechCrunch actually flagged that exact caveat in their reporting. NVIDIA benefits enormously from this narrative, but the numbers are hard to dismiss. NVIDIA says its latest data center superchip is more than 30x faster for AI inference workloads than its previous generation. That's not a marginal improvement. That's a generational leap in a single product cycle.
30x in one generation.
Yeah, and it's not just NVIDIA making this case. There's independent research from an organization called Metiar that found AI agents' ability to complete tasks has doubled approximately every 7 months over the past 6 years. That is more than 3 times the rate of Moore's law. And what's striking is that over the most recent 4 months of that study, it doubled again, suggesting the curve might actually be steepening.
Wait, so it's not just fast, it might be getting faster?
That's what the data suggests. And Huang has a framework for why. He says there are now 3 active AI scaling laws running in parallel. Pre-training, which is the initial phase where models learn from massive datasets, post-training, which fine-tunes models using human feedback, and test-time compute, which gives models more time to essentially think through a problem during inference. Moore's law was 1 lever, AI has 3.
That's a really useful frame. So it's not just better chips, it's better chips plus better training methods plus smarter inference, all compounding at the same time.
Exactly. And that's why the numbers coming out of EE Times are so staggering. Training compute for large language models has grown by about 750x every 2 years. The size of those models, measured by parameter count, has grown by 410x every 2 years. Compare that to Moore's law's 2x every 2 years, and you start to understand why people are using words like hyper-Moore's law.
750x every 2 years. That's not a doubling. That's almost incomprehensible.
It really is. And it creates this massive tension because the hardware side, the physical chips, cannot keep up with what the software side is demanding. EE Times put it plainly, the semiconductor industry cannot keep up with AI's compute, memory, and interconnect requirements. So you have this race where the ambitions of AI are outrunning the physical infrastructure that supports it.
So there's a bottleneck forming, and I've been reading about something called the memory wall. Is that what we're talking about here?
Yes, and this is genuinely one of the most underappreciated constraints in AI right now. The World Economic Forum published a piece on this in May 2026 that laid it out really clearly. Most computers still use what's called the von Neumann architecture. Memory and processing are physically separate. Every time a calculation happens, data has to travel from memory to the processor and back. For AI, which depends on enormous numbers of parameters accessed repeatedly, that back and forth becomes incredibly expensive in terms of time and energy.
So it's like having a massive library, but the librarian has to physically walk to the shelf and back every single time you need a book.
That's a great way to put it. And the scale of the problem is wild. The World Economic Forum noted that language processing models grew 5,000-fold in size over just 4 years. So the librarian is now walking miles for every single lookup. The energy cost alone is becoming a serious constraint.
5,000-fold in 4 years? Okay, so how do you even begin to solve something like that?
So researchers at Purdue University and Georgia Tech published a paper in Frontiers in Science in December 2025 that laid out the main approaches. The most promising is something called compute in memory, or CM. You integrate computing capabilities directly into the memory system so the data doesn't have to travel at all. The World Economic Forum also highlighted brain-inspired approaches, like spiking neural networks, which process information the way neurons do, in bursts, only when needed, which is far more energy efficient.
So we're literally looking at chips that are inspired by how the human brain works.
Neuromorphic chips, yeah. And there's also the hardware innovation happening at the chip design level, 3D stacking, which places memory directly on top of processing elements, reducing data transfer bottlenecks by 10 to 100 times, according to the research. Chiplet architectures that combine specialized components like building blocks. These aren't science fiction. They're in active development right now.
And on the software side, there are algorithmic innovations too, right? It's not all hardware.
Right, and this is actually where some of the most interesting gains are happening. Things like transformer architecture, mixture of experts models, and quantization techniques have enabled efficiency gains that are completely independent of hardware improvements. You can make a model smarter and cheaper to run without touching the chip at all. That's a fundamentally different kind of progress than Moore's law ever offered.
Okay, I want to zoom out for a second because I think there's a really important question here. Is all of this progress actually showing up in real-world AI capability, or is it still mostly benchmark numbers?
The Stanford 2026 AI Index report is probably the most comprehensive answer to that question. And their headline finding is unambiguous. AI capability is not plateauing. It is accelerating and reaching more people than ever. On a key coding benchmark called SWE Bench Verified, performance went from 60% to near 100% in a single year. That's not a marginal gain, that's a system going from pretty good to essentially solving the problem.
Near 100% on a coding benchmark in 1 year. That's the kind of number that makes you stop and think.
And Stanford also found that several frontier AI models now meet or exceed human baselines on PhD-level science questions, multimodal reasoning, and competition mathematics. Industry produced over 90% of notable frontier models in 2025. Organizational adoption reached 88%. 4 in 5 university students now use generative AI. This is not a niche technology anymore.
Okay, I have to bring up something from the Stanford report that I found genuinely fascinating and a little bit funny. They have this concept called the jagged frontier of AI. Can you explain that?
Oh, this is one of my favorite things in the whole report. So, Google's Gemini DeepThink earned a gold medal at the International Mathematical Olympiad, one of the hardest math competitions in the world. And yet, according to Stanford, the top AI model reads analog clocks correctly just 50.1% of the time. That's basically a coin flip.
So it can solve problems that stump the world's best mathematicians, but it cannot tell you what time it is from a clock face.
That's the jagged frontier. AI capability is not a smooth curve. It's these wild peaks and valleys where the system is superhuman in some areas and genuinely baffling in others. And I think that's actually a really important thing for people to internalize as they think about where AI is going.
It's a good reminder that AI is getting smarter is not the same as AI is getting smarter in the ways we expect or need.
Exactly. And that connects to something the McKinsey 2025 State of AI survey found. Nearly 9 out of 10 organizations are regularly using AI, but nearly 2/3 of them have not yet begun scaling it across the enterprise. There's this huge gap between we're experimenting with AI and AI is actually transforming how we operate. The technology is accelerating faster than most organizations can absorb it.
That's a really interesting tension. The hardware is racing ahead, the models are racing ahead, and then you have most organizations still in the pilot phase.
McKinsey found that 64% of respondents say AI is enabling their innovation, but only 39% report actual bottom-line impact at the enterprise level. So the promise is real, the tools are real, but the translation into actual business value is still lagging. And that gap is going to be one of the defining challenges of the next 5 years.
Let's talk about the geopolitical dimension here, because I think it's impossible to talk about AI hardware without talking about what's happening between the US and China. The Stanford report had some pretty striking findings on that.
Yeah, and this is where things get genuinely complicated. Stanford's 2026 AI Index found that the US-China AI model performance gap has effectively closed. US and Chinese models have traded the lead multiple times since early 2025. In February 2025, DeepSeek R1 briefly matched the top US model. As of March 2026, Anthropic's top model leads by just 2.7%. That is a razor-thin margin.
2.7%, that's basically a tie.
And on the hardware side, Reuters reported in May 2026 that Chinese companies like Huawei and Alibaba are racing to build chips that can replace NVIDIA in the Chinese market. Alibaba's chip design unit unveiled a chip called the Zhenwu M890 and laid out a multi-year roadmap. Huawei had already published a similar roadmap running until 2028. The goal is explicitly to build a post-NVIDIA AI chip ecosystem inside China.
And there's a really interesting wrinkle in the NVIDIA China story that I want to flag. Jensen Huang claimed that NVIDIA's chip shipments to China were essentially zero after export controls. But Reuters found something different.
Right, and this is a significant discrepancy. According to Reuters, NVIDIA actually shipped 2.2 million AI accelerators to China in 2025, representing a 55% market share. That directly contradicts Huang's public statements. So even in the middle of a geopolitical chip war, the flows of hardware are more complicated than the official narrative suggests.
And then there's the TSMC issue, which Stanford flagged as a kind of single point of failure for the entire global AI hardware supply chain.
This is one of the most underappreciated risks in the whole AI story. Stanford found that the United States hosts 5,427 data centers, more than 10 times any other country. But almost every leading AI chip is fabricated by a single company, TSMC, at a single foundry in Taiwan. The entire global AI hardware supply chain runs through one facility on an island that is at the center of one of the world's most significant geopolitical tensions. A TSMC US expansion did begin operations in 2025, but the concentration risk is still enormous.
So, the most powerful technology in the world is dependent on one factory in one of the most geopolitically sensitive places on Earth. That's a sentence that should make everyone a little uncomfortable.
It's a real systemic vulnerability, and it's one of the reasons why you're seeing such aggressive investment in domestic chip manufacturing and why the race between Huawei, Alibaba, and others in China is so intense. Everyone is trying to reduce their exposure to that single point of failure.
Let's bring this back to the 5-year outlook. If you're looking at where AI is headed by 2031, what does the data actually suggest?
A few things stand out. First, the investment trajectory is staggering. According to data cited in AI Development Trend Analysis, U.S. private investment in AI reached $109 billion in 2024 alone, roughly 12 times higher than China's investment and 24 times the UK's. That capital is going to keep compounding into capability.
109 billion in a single year. And that was 2024. We're now in 2026.
Right. And on the agent side, McKinsey found that 62% of organizations are at least experimenting with AI agents, systems that can take actions autonomously, not just answer questions. That's a qualitative shift in what AI is being asked to do. We're moving from AI as a tool you query to AI as an agent that operates on your behalf.
And Stanford's data on AI agents is pretty striking too. They went from 12% task success to around 66% on OS World, which tests agents on real computer tasks across operating systems.
Yeah, 12% to 66% is a massive leap. Though Stanford is careful to note, they still fail roughly 1 in 3 attempts on structured benchmarks. So we're not at fully reliable autonomous agents yet, but the trajectory is clear. And the hardware innovations we talked about, compute and memory, neuromorphic chips, chiplet architectures, those are all aimed at making these agents faster, cheaper, and more deployable at the edge, in devices, not just in massive data centers.
The edge piece is interesting, the idea that AI moves out of the cloud and into the device itself. Medical devices, autonomous vehicles, rescue drones, the World Economic Forum specifically mentioned those as use cases where you can't wait for a round trip to a data center.
Exactly. And that's where the memory wall problem becomes really acute. A rescue drone or a medical device doesn't have the luxury of massive bandwidth and power. It needs AI that can run efficiently on constrained hardware, make fast decisions locally. That's why the research coming out of Purdue and Georgia Tech on compute and memory and neuromorphic approaches is so practically important. It's not just academic. It's about whether AI can actually work in the real world at scale.
I want to come back to something you said earlier about the 3 AI scaling laws that Huang described: pre-training, post-training, and test time compute. Because I think there's a counter-argument worth addressing. Some people are saying AI progress has stalled. How do you square that with everything we've been discussing?
It's a legitimate debate. The skeptics point to the fact that pre-training, just throwing more data at bigger models, does seem to be hitting diminishing returns. But Huang's argument, and the Stanford data supports this, is that pre-training is only one of 3 active scaling dimensions now. Post-training and test time compute are still yielding significant gains. The SWA bench jump from 60% to near 100% in a year happened largely through improvements in those latter 2 areas.
So the engine isn't stalling, it's just shifted gears.
That's a good way to put it. And Huang's point about innovating across the entire stack simultaneously is key. Moore's law was about one variable, transistor density. What's happening now is multidimensional. You're improving the chip, the architecture, the training method, the inference method, and the algorithms all at once. That's why the aggregate progress is so hard to benchmark with any single metric.
And that's actually what makes this moment genuinely different from previous tech hype cycles. It's not one breakthrough, it's a bunch of compounding breakthroughs happening simultaneously.
And the applications are starting to reflect that. Google DeepMind's research page shows AI being used to improve breast cancer detection, preserve genetic information of endangered species, model weather at unprecedented accuracy with WeatherNext 2. These aren't demos, they're deployed systems producing real-world results. That's a different category of impact than what we were talking about even 3 years ago.
So when you step back from all of this, the hardware race, the memory wall, the geopolitics, the agent leap, the jagged frontier, what does it actually come down to?
Here's what I think this really comes down to. Moore's law was a prediction about one thing, transistors. What's replaced it is not a single law, but a multi-front acceleration that's harder to track and harder to predict. The EE times framing is useful here. AI's compute demands are growing at 750x every 2 years, while the hardware can only scale so fast. That gap has to be closed through architectural innovation, algorithmic efficiency, and new paradigms like compute and memory. The next 5 years will be defined by how well those solutions keep pace with the ambition.
And on the human side, the McKinsey finding that 2/3 of organizations haven't even begun scaling AI across their enterprise, that's the other gap that needs closing.
Right. The technology is accelerating faster than institutions can absorb it. And that's not a criticism, it's just the reality of how transformative technology diffuses. The companies that figure out how to close that gap between experimentation and enterprise-level transformation are going to have an enormous advantage. McKinsey found that the high performers, the ones actually seeing bottom-line impact, are the ones redesigning their workflows around AI, not just bolting it on.
So the lesson isn't just use AI, it's redesign how you work around AI.
Exactly. And the Stanford 2026 AI Index makes clear that the benefits of AI won't be evenly distributed unless development is guided thoughtfully. The capability is accelerating. The question is whether the wisdom to deploy it well keeps pace. That's the real race of the next 5 years. Not just chips versus chips, but human institutions versus the speed of change.
That's a really important note to land on. We started this episode talking about a 60-year-old law being lapped. And what we've actually uncovered is that the replacement isn't one new law, it's a whole new physics of progress, happening on multiple fronts at once, with real constraints and real stakes.
And the constraints are real. The memory wall is real. The TSMC concentration risk is real. The gap between AI capability and organizational readiness is real. But so is the trajectory. AI agents going from 12% to 66% task success. Coding benchmarks going from 60% to near 100% in a year. Training compute growing 750x every 2 years. These are not small numbers.
And yet, and I love this, the most powerful AI system in the world still can't reliably tell time from a clock face, which is maybe the most honest summary of where we are.
Gold medal at the Math Olympiad. Coin flip on the clock. That jagged frontier is going to be with us for a while. And honestly, understanding that, knowing where AI is genuinely superhuman and where it's still surprisingly fragile, is probably the most useful thing anyone can take from this conversation.
So here's what to actually do with all of this. Pay attention to where AI is being deployed in your field, not the demos, the actual deployments. Watch the hardware story, because the memory wall and the TSMC supply chain are going to shape what's possible. And if you're in an organization still in the pilot phase, McKinsey's data is pretty clear. The gap between experimenting and transforming is where value gets left on the table.
And keep the jagged frontier in mind. The hype will tell you AI can do everything. The reality is it can do some things at a level that genuinely defies belief, and other things it can barely manage. Knowing the difference is what separates people who use AI well from people who get burned by it.
We started by saying a 60-year-old law got lapped. But here's the thing. Moore's law didn't just describe progress. It created the conditions for the very AI that surpassed it. So maybe the real story isn't that AI broke the rules. It's that AI is the thing Moore's law was always building toward. Thanks for listening to Copilot Podcasts. The clock is ticking, even if AI can't quite read it yet.